Hi everyone. Okay, we've looked at two really good challenging examples of integral test. Every example of integral test is challenging. Honestly, they take a long time, and there's sometimes that tricky logic that we saw in part B. We're now going to look at something that is a natural consequence of the integral test called the P-series. And it's going to start off very simply. So we're going to kind of discover this through some examples. Let's look at this very simple series, n equals 1 to infinity for 1 over n squared. So we're going to walk through quickly what the integral test would say about this series, whether it converges or diverges. If you like, feel free to pause the video and explore that with the integral test on your own. If you would rather just watch, I'm going to get right to it. If we were in class, I think just for the sake of time, we would probably all just go through it together. But if you want, because you've got the time on your own, explore this, hit pause, and do that. Okay, I'm going to get started. All right, so the first question is about the function, right? F of x equals 1 over x squared. Sorry, that's kind of coming through a little bit weird. I think it's the lighting at that angle. Okay, maybe if I pull it down a little bit, that'll be a little bit better. F of x equals 1 over x squared. Okay, so if we're going to look at the three conditions, all right, is that function positive for x greater than or equal to 1? Sure is. Enough said. Is that function continuous? Yep. Is that function decreasing? Oh man, that's really kind of hard on the eyes there, but okay. We will quickly check with the derivative. Our derivative is negative 2 over x to the third. You might show some steps getting there. But okay, for x greater than or equal to 1, we're always going to have a negative over a positive. Yep, that is always decreasing. That derivative is always negative. So we are good to go. We have satisfied the conditions. Now here on the other side, we're going to take a look at the integral. So we're going to begin with the integral of our function from 1 to infinity, 1 over x squared. Well, that's a little bit easier than the ones we were doing a moment ago. This antiderivative would be negative 1 over x. From 1 to t, as t goes to infinity. Plugging in, I've got negative 1 over t minus negative 1 over 1. So, okay, there you go. Negative 1 over t plus 1. As t goes to infinity, what happens to that right there? As the denominator gets bigger, that goes to 0. So the answer to our integral is simply 1. Wow, that's incredible. The area from 1 to infinity underneath 1 over exactly 1. That is something. Okay, anyway, that's not really the point. The point is the integral converges. So what can we say about the series? Let's be really clear. The integral converges. Therefore, the series converges. And if I really wanted to be extra correct, I would say the series converges by the integral test. Because this is just a demonstrative example, I think we get it. Okay, it converges. Let's take a look at this one. 1 over x to the third. Starting at n equals 1. Hey, if you like, pause the video. Go ahead and tackle this one by the integral test on your own. Be sure to check the three conditions. Okay, so turns out the three conditions are satisfied. The derivative is not much different than the previous one, and it's continuous, it's positive. Let's just cut to the chase. In these demonstrative examples. Okay, so we're just going to jump right into it. We're going to take the integral from 1 to infinity, 1 over x to the third. That antiderivative would have been negative 1 over 2x squared from 1 to t. And as we take that limit, as we plug, I'm really skipping steps here. As we plug the t's in, plugging in negative 1 over 2t squared, as t goes to infinity will be 0. Plugging in the 1 and subtracting will give us an answer for our integral of positive 1/2. And so that integral converges, and so the series converges as well. So we showed it for 1 over n squared, starting n equals 1. We showed it for, oh my goodness, look at that. That was supposed to be an n. How long have I been teaching this and made that mistake? 1 over n to the third from n equals 1. So 1 over n squared, 1 over n to the third. It looks like if we keep making the numerators, if we keep making the powers in the denominator bigger, it's just going to continue to converge because the values get so much smaller so quickly. So let's go backwards. Let's make it 1 over n to the first from n equals 1 to infinity. Turns out this series has a special name. It's called the Harmonic Series. Turns out the Harmonic Series, that name, harmonic, kind of sounds like harmony, music, right? That's not a coincidence. Not that I'm a musical person or I've studied that, but I know just enough about math to know that there's a connection between the mathematical analysis of musical notes and this series. Don't ask me anything more than that. Okay, let's take a look with the integral test. Hey, if we took the corresponding function, it would be positive, continuous, and decreasing for n greater than or equal to 1. So let's skip all that and just jump right to the integral, and it looks like I've got it all right there in one shot across the page. All right, so 1 over x from 1 to infinity. Well, that would be antiderivative is the natural log. Interesting. From 1 to t, t going to infinity, so plugging in. And gosh, sorry, this is just tough to read. It's like blue on the screen. Plugging in the t, plugging in the 1. And oh, as t goes to infinity, the natural log of infinity is infinity. Oh, wow. This series actually diverges. Now, this really, if you're thinking through, what these series are and intuitively, this should just be like shocking. Like we should all be on the floor after hearing that the series 1 over n from 1 to infinity diverges. What is that? Clearly, we can see it with the integral test. The integral diverges. So the series must do the same. But really think, what does that mean, right? So you're telling me if I add up the terms, if I add all infinitely many terms, they're going to add to infinity? How is that? Why? Let's investigate it from an adding the terms perspective. Okay, so I'm going to write this, and you see those brackets I've written underneath. Ignore those for the moment. We'll explain that in a second. Okay, so what's happening here? Starting at 1, well, there's the first term. I'm going to add the second term, third, fourth, fifth, sixth, right? I'm going to keep adding these fractions. And you're thinking to yourself, you're trying to tell me that if I add all of these fractions together and I keep adding, it's going to add up to infinity. Well, they're getting smaller, right? If I took the limit of the nth term, that would go to 0. It turns out, yes, they're definitely getting smaller. as we go term to term. But if you keep adding, it will just continue to get bigger and bigger and bigger without bound, we say. And if we add all infinitely many terms, it will add to infinity. Like, what? Can you help me out with that? Because I don't see it. It seems to me like it should level off somewhere. I mean, eventually we're going to be adding 1 over 1 million, 1 over 1 billion, right? I mean, how can that keep adding up to infinity if we keep going? All right, here's the thinking. The 1 is kind of a special case. So just sort of ignore the 1. The rest are going to follow a pattern. All right, so whatever these other ones add up to, just know you have to then add 1 to it. So we're going to sort of skip that. Begin at the half. All right, so at n equals 2, you've got a half. Take a look at the next pair where the bracket is. I've got 1/3 plus 1/4. Would you agree that when you put these two together, you get something bigger than 1/2? When you add 1/3 and 1/4, that's bigger than a half, right? If it was 1/4 plus 1/4, it would be a half. But 1/3 plus 1/4 is larger than 1/2. Okay, so I added a half, but then I added something that's bigger than a half. And it took 2 terms, but we did it. Okay. Then look at the next group of 4. This is also bigger than 1/2. Right? If all of these were 1/8, 1/8, 1/8, 1/8, 1/8, that would be 4/8, 1/2. But we've got things that are larger, 1/5, 1/6, 1/7, right? This is bigger than a half. Now, it took 4 terms to do it, but who cares how many terms? I got infinitely many terms to work with. So I got the half, but then something bigger than a half, and then something else bigger than a half. If I was to look at another set, I would need 8 of them, but the next 8 would be something bigger than a half, right? If I keep adding even 1/2s, if I had a half plus a half plus a half, and I kept adding halves, that would be infinity. But I've got something bigger, and and I don't know the nature of the relationship between these two. That doesn't matter. This is bigger than the half. This is big. I keep adding at least 1/2 for every group. Now the groups end up getting huge eventually because we're doubling every time, but who cares? I've got infinitely many terms I'm working with. So I can tell and I can make sense of it even from this perspective, let alone from the test, that all those infinitely many are going to just keep getting bigger and bigger and bigger and bigger. And really, like, what just blows us all away, the terms are getting smaller. That limit is 0, yet it still finds a way to diverge. They're getting smaller, the terms, but they're not getting small enough, fast enough to eventually converge. They still add up to infinity. That is crazy. And there's like your prime example of when you take a limit to 0, we have no idea. It might converge, it might diverge. Right? We need another test. Luckily, we're learning more as we go. Okay, so here's the P-series test. It has to do with, I'll just show you the whole thing. It has to do with powers of n in the denominator. So 1 to infinity, 1 over n to the p. Now again, we say it starts at 1. It doesn't have to. It could start at 2 or 3 or 4. Really, the one series that it must start where we say is the geometric series. Geometric has to start at 0, but any other test can start wherever you like. That's the default. Okay, so we say 1 to infinity, 1 over n to the p. If p is greater than 1, if it's 2 or 3 or 4, then that's going to converge. Those are the first examples we did with n squared and n to the third. Turns out, though, just a tiny bit bigger than 1. If it was 1.1, it would still converge. 1 is the cutoff. It's like the critical value, we say. If it's 1 or anything smaller, then our series diverges. Okay. So in a sense, it's almost like opposite. It's very similar to geometric series, but yet opposite, right? So for geometric, it was if r is greater than 1, it diverges. If r is less than or equal to 1, it converges. Here it's the opposite. P bigger than 1, right? P less than or equal to 1. Actually, I misspoke. If r equals 1, it diverges. Anyway, you get the idea. So let's do a couple of quick ones. I think I just have one, actually, with the p-series test. Does this converge or diverge? N equals 1 to infinity, 2 over n to the 5 over 2. What do you think? Well, I noticed this 2 on top. Well, that's all right. I could really move the 2 out here and call it 1 over. So I'm going to double everything. That's not going to change if it converges or diverges. The essence here is the power, right? Well, is that power, how is it compared to 1? Well, 5 halves, p equals 5 halves, we would say. That's bigger than 1. So this converges, simple as that. This converges by the p-series test. We don't have to take any integrals. We don't have to check the function conditions. We've got a new test specifically for this simple case. Just check the power. It's bigger than 1, so we know it converges. And of course, we cite the test. Hey, at this point, we know 5 tests: geometric, divergence, telescoping series, integral test, and now p-series test. That's the end of 11.3.